Hey everybody, it's Miss A again. Welcome back to another week of virtual learning. Just want to have a little reminder here that school's almost out. We've got 7 weeks left. It's not like I like to count down starting too early because when numbers are too big, it's not as exciting, but I figured that 7 weeks left is definitely something to celebrate. So let's get excited. I don't know about you guys, but I'm looking forward to this being me in a couple of weeks, grilling and chilling outside in the backyard, enjoying some warmer weather. So I know that this is what's keeping a smile on my face, warmer days to come and nicer weather to be enjoying. So I hope you guys are keeping something in mind to keep a smile on your face. All right, so this week's goal is to perform operations on functions. That means we're going to add, subtract, multiply, and divide functions. This is going to be very similar to the times in your math classes where you have added, subtracted, multiplied, or divide different polynomials or expressions. This is going to look very similar, but the directions and the notation are going to be a little bit different. And then also we're going to create and evaluate composite functions. So this is going to go based around the idea of substitution, and we're going to create them, but we're also going to evaluate. So sometimes we're going to be creating expressions, and other times we're going to be evaluating for a numerical value. Either way, before we get started, I do want to let you guys know, grab your colors. 3 colors is what you need. If you want to do something like a highlighter, that's fine, or something more like a pen, a pencil, markers, thin markers, or colored pencils, whatever you guys feel comfortable with, but we are going to be writing. So make sure that you're comfortable writing with this implement that you choose. I don't want you to choose like a big old fat highlighter and then you're having trouble looking at what you're writing, okay? So feel free to pause the movie right now to go get your supplies. Calculators won't hurt, but certainly definitely need colors the entire time. All right, this is how we're going to break down this week's video. It's going to be in 3 parts. I'll come back to this every time we finish a part of the video so that you guys can take a look at what your work is going to be corresponding to the different parts of this video. So let's go ahead and get started. Part 1. All right, so part 1 is about function operations, all right? And this is the only part that we're looking at for function operations in this video. We're going to be taking a look at adding, subtracting, multiplying, and dividing. And as you guys know, sum, difference, product, and quotient in order are those math terms, just in the fancier way of saying them, right? Because we're all mathematicians here. As you guys are taking down these notes, something that I want you to take a look at is essentially what I've done is if I want to add 2 functions, I can write that out as what I have here on the left-hand side of this equal sign or what I have here on the right-hand side of this equal sign. Same thing if I want to subtract, there's 2 different ways to write it, the left or the right. Product, again, left or right, and quotient, either the left side or the right side. The reason I'm pointing out that there are 2 different ways to write the same thing is because depending on your teacher, when you go to college, your professor, the textbook that you're using, the YouTube video you're watching, whatever the case might be, there are preferences sometimes for the different way that you can write out these function operations. Also, not to mention that one of the things that might come into play is the exam that you're taking. For instance, the SATs, college entrance exams, the ASVAB exam for those of you looking to go into the armed forces, but they all mean the same thing. Most important thing to recognize here is the operation. No matter how I write this, we're seeing an addition symbol for adding, subtraction for subtracting, multiplication symbol for multiplying, and a division bar or fraction bar for dividing. Something else I would like to point out to you here is, if you guys aren't already familiar with the notation that's being used here, is that it's function notation. So I'm giving the example of addition, the 2 different ways to write it out. If I want to write f plus g of x, or if I want to write it out as f of x plus g of x, remember, this is just the name of a particular function. This is the name of another particular function. Same thing here. It's just it's split up for notation. This extra x that's like hanging around, remember, is just part of function notation. It does not mean multiply by x. It doesn't mean add these two functions, oh, and then multiply everybody by x. That's a common mistake that I see because a lot of us see parentheses with an x and we think of multiplication, but remember, this is function notation. So pay attention to the order. F is coming first, G is coming second, or in this case, F is coming first, G is coming second. And then also just pay attention to the operation that they're writing. That's really all that you need to pay attention to in order to avoid a silly mistake. But this is the notation that we're going to use in order to combine these functions in this way. So get your colors ready. Feel free, again, to pause at any point during this video because what I have done is, I'm just going to adjust my focus here, guys, for a second. It looks a little bit blurry to me. What I have done is, in advance, I have color-coded a little bit of this and set up some of the problems just so that it's a little bit easier for you guys to view and also to save a little bit of time on this video. Don't want to make it too long for you. So these questions where you are being asked to perform operations are going to say, given that, and they're going to list two functions. F of x is this function here, and g of x is this function here. They want you to find f of x plus g of x and express that result in standard form. Hey guys, listen, standard form, that's really important. Remember what standard form means. Here's an example. This function here is written in standard form. Highest exponent of our variable is listed first, and then it goes down the list in decreasing order. So x squared, x to the first, and then no x's or x to the 0. Same thing here. This function is written in standard form, x to the first, and then no x's or x to the 0. So make sure that you're writing your answer in standard form because if you don't, especially in Delta Math, it will mark your answer incorrect because of order. But what they're asking us to do here is add our two functions. We need to take function f and write it down first and then add the function g to it. Throughout the course of this video, I am keeping consistent with my function f always being pink and my function g always being blue. So if that's something you want to stay consistent with as well, please keep that in mind. Anything that's neutral, I chose a third color for, but your pen or pencil is totally fine for the neutral stuff. Anyway, so here we go. I have function f listed first plus my function g. I didn't use any sort of parentheses or anything in this problem because remember, addition does not change anybody's sign. There's no need to distribute the symbol or anything. Adding just means combining like terms. So it's exactly what I'm going to do here. For like terms, x squared does not have any like terms. So I'm just going to rewrite that, x squared. I've got negative 17x here and a positive 1x, which gives me a negative 16x. And then I've got positive 70 and a negative 7, and together that's going to give me a positive 63. And that will be my final answer. It really is that simple. I'm just taking one function and adding it to another, also known as combining like terms. All right, let's take a look at a second example here. Same idea, but I've got new functions still named f and g, and now they're asking me to subtract these two functions. So I'm going to write out function f first, then I'm going to subtract away my second function g of x. Now, notice that I used parentheses this time because when I subtract, remember, I have to subtract every term in that function. And if that's the case, I kind of have to treat this like a -1, which means that I need to distribute the negative sign to each of these terms. So I've got x squared minus 10x plus 24. And then I'm going to distribute. This is going to be minus x. And then a negative times a negative gives me plus 6. Now from here, just like the previous problem, it's a matter of combining like terms. So I've got x squared who has no like terms. I've got negative 10x and negative 1x giving me negative 11x. And I've got 24 and 6 giving me 30. And this is my final answer. Those are the two easier of the operations. Just please make sure that with subtraction, you do use parentheses for that second function. Now let's take a look at multiplication and division. These guys are a little bit more challenging here. So for multiplication, you might see that I wrote a note up here about Delta Math. I want to show you guys something that Delta Math does just so that you don't get confused and think you're going cuckoo crazy or something. But essentially, it's the same setup. They're giving us two different functions, f and g. They're asking us to multiply them this time. They want f to be listed first and g to be listed second, so it's exactly what I did. They still want our answer in standard form, so we're going to keep that in mind as we go along. Now remember, multiplication is a special property. I know that when you're looking at this, you might think, wow, I have to distribute all three of these terms to all two of these terms. I kind of like distributing the smaller guy over the bigger guy, like x times each of these terms, and then -2 times each of these terms, which if that's what you want to do, that is okay. But remember, what property allows us to change the order of what we want to multiply and we're still going to get the same answer? Let me give you an example. 3 times 2 is going to give me 6. 2 times 3 is still going to give me 6. What is the name of that property? If you said commutative property, you are correct. So if you prefer to distribute the little guy over the big guy, that's what I like to do, and that is what I'm going to do here. So if I multiply everybody by x here, that means that I'm going to bump up everybody's exponent by 1. So I've got x to the third plus 5x squared minus 14x. If I then distribute the -2 to each of these terms, I like to stack my like terms just so that you guys know if you're not familiar with that. I'm going to get a -2x squared minus 10x plus 28. I like to do this stacking method just because it kind of combines my like terms already for me instead of looking at one long line of terms. So I've got x to the third. Together here, I've got plus 3x squared. Together here, I have minus 24x and then plus 28, and this is our final answer. What I want to show you about Delta Math is that the way that they multiply is they don't show this distribution. They actually show it in a table form. So they write out each of their polynomials like this on the edge of a table, and they multiply to get these values inside the boxes, and then they combine the like terms to get the same answer we do. But if you guys saw this box, it is totally not necessary. It is the same thing as doing distribution. I just didn't want you guys to get confused. All right, example number 4, we are dividing. Again, new function f and new function g. They're asking us to divide, and if you notice, I did write a division bar here because this sign, although it's appropriate just to let somebody know that we are doing the process of division, as you guys know at this point in your math lives, we really need to be working with an actual fraction bar or division symbol like this. So the problem here is that if you notice, I did put parentheses around each of these expressions, and the reason is because some of us might be tempted to start canceling out or crossing out these x's, or maybe reducing 35 over 5. You can't do that. Addition and subtraction symbols are like little chains, and they link these different terms to each other. So unless I can cross out an entire expression, I can't actually start crossing anything out. So with that being said, take a look. We've got a quadratic here. We've got a expression in our denominator, where this expression reminds me of how this expression gets broken down, right? It's one of our like little binomials for, hopefully you were looking at my little subtle hint over here on the side. Yes, your favorite F word, factoring. So let's try and factor what's going on in the top here and create two binomials, because then maybe this will actually be able to be reduced here. So we're going to look at, if we set up our X method, what two numbers multiply to give me -35, but then add to give me -2. That would be 5 and -7. These guys are my magic numbers. So if I rewrite this top expression here, I would have x plus 5 times x minus 7, and hold on a second, take a look. That means that I would have the same identical expression in my numerator and denominator, and then I would be able to reduce and get a final answer of x minus 7. So for the division problems, always look for an opportunity to factor in order to reduce. this concludes part 1 of the video. So if you're ready and you're chunking your work, my suggestion is that you take the course of 2 days to kind of work through this, and you guys can go ahead into Delta Math, into arithmetic operations on functions. For my kids, I'm introducing quizzes or quizzies. I'm not 100% sure how to pronounce this because it's so new to me, but I'm introducing them as enrichment. They are in our Google Classroom, and you guys can take a look at those. I'm going to challenge you guys to try and do that this week. All right, part 2 of our video. Part 2 of our video is focusing on composite functions. It's going to be broken up into 2 parts. One where we are just creating composite functions, and then the other part where we are evaluating them. So composite functions are written or defined as f of g of x, or I mean, any of these letters can be interchanged or changed at all to be different letters. But again, there's 2 ways to write the same thing. This little open circle is kind of like a degree symbol, how we write it as an open circle. It's not closed. That would mean multiplication, so be careful there. But it means f of g of x. So, you know, just kind of how you guys, if you were to just literally look at this g of x here, you guys know that this is g of x because that's how you say function notation, right? So now this little symbol is also standing for the word of. So you've got f of g of x, or you've got f of g of x. So these parentheses actually take the place of the word of. I've written out how you say it right here, f of g of x, if it's in that order. Obviously, if there's different letters, then you would have to say it a little differently. How do we even do this? Like, this is obviously showing us that we're going to have to substitute, that this is getting placed inside of this function. Or if I were to change this value from a variable to a number, numerical value, this number or value would need to be placed inside of this function. And then ultimately that answer would have to be placed inside this function. So we're going to be doing a lot of substitution. Now, both of these notations are very popular, but I do want to point out that I do like this notation to start off with because of the visual of it, and we're going to go through both examples together, don't worry. I do want to point out the simple fact that this does change the domain of your functions, and that does play a larger role in some of the bigger topics that you look at in your mathematics courses, especially ones where you're going to be moving forward to maybe pre-calc, calculus, anything of those upper level type of math courses. And all it's saying is that x is the domain of g and g of x is the domain of f. We know that domain is kind of like a fancy word for inputs, and that kind of makes sense here considering we're plugging into one another. So x is the input or domain of g. All of this, g of x, is the input or the domain of f. So just to kind of get this definition out in some simple everyday terms instead of math terms. I did write a little note down here just to help us out here, the difference. Part 1 of this section on composite functions, which is technically part 2 of this video, is going to be focusing on what I wrote over here on the left, which is f of g of x. So when I see a variable here, it means I'm going to create a composite function. If I'm creating a composite function, that means my answer is going to look like an expression. It's going to have x's, variables inside of it. Versus the next part of this video, which is going to be part 3, where I'm going to have a numerical value in here, which means that the problem is asking me to evaluate the composite function. And if that's the case, that means that my answer is going to actually be a numerical value, not an expression. All right, so that's the difference between these 2 questions. All right, so let's get started. So these guys, composite functions, when we are just creating a composite function, I like to call these jelly donuts. Why? Because, well, when you're making a jelly donut, first you make the actual donut itself, and then you fill it with jelly. That's exactly how composite functions work. They're asking us to express our answer as a polynomial in standard form. And they're asking us here, as you can see, what we're going to do. They're asking us f of g of x. I've rewritten it in that other form because I think that visual might be helpful, f of g of x. So what does this mean? It means that I'm going to plug my function g of x into my function f of x, or again, over here, plug g of x into my function f of x. So how does this relate to jelly donuts? Well, like I said, Donuts have to be made first, and then the jelly gets inserted. So who here is acting like the jelly and who's acting like the donut? Well, whoever is on the outside or listed first is going to act as the donut. That needs to get set up first. So we're going to create our donuts and then we're going to fill it with jelly. Whoever's on the inside or all the way over to the right is going to be your jelly. So let's just clarify. F of x is my donut. G of x is my jelly. I'm just writing myself a note for this problem. So first I have to make my donut. That means I'm going to take my donut function, which in this case is f, and everywhere I see an x, I'm going to put a set of parentheses because I'm making a jelly donut. So I need to provide a space to be filled with jelly. So I've got 4 times a quantity, that's taking the place of my x, plus 2. Now I'm going to fill my donut with the jelly. In this case, my jelly is G. So I'm going to plug in this entire expression into my set of parentheses. So I've got x squared plus 5x plus 11. Now, believe it or not, guys, the hard part's over. You've created your jelly donut. You're good to go. Now you just need to carry out order of operations and combining like terms. So we are going to distribute this 4 to each of these terms, which is going to give me 4x squared plus 20x plus 44. Don't forget that you've got this plus 2 at the end. The only 2 like terms I have are these 2 guys at the end. 44 plus 2 is going to give me 46. So my final answer in standard form is going to be 4x squared plus 20x plus 46. And we're done. All right, let's try another example. Again, if I'm going too fast, please stop the video and rewind and listen again. Just want to save on time for this video. So another example, they're asking us this time g of f of x, or I rewrote it in the other form, g of f of x. This means f of x is our jelly that's getting put into g of x, which is our donut. So f gets plugged into g. So I'm going to write myself a note. G is my donut. F is my jelly. And remember, we have to make the donut first and then fill it with jelly. So if you notice here for our donut, we've got a negative sign in front of this x. So I'm going to actually write that as a -1 because we got to be careful with that. You don't want to miss that, guys. So -1 times some quantity minus 15. Okay, because I am going to need to distribute that. Now I'm going to fill my donut with the jelly, which is my function f of x. So I've got 3x squared plus 4x plus 12. And again, the hard part is over. You've created your jelly donut, and now you just need to follow order of operations and combine like terms. So I'm going to distribute this negative sign, or this -1, which means everybody is now going to turn into the negative version of themselves since they're positive. So -3x squared minus 4x minus 12. Don't forget you've got this minus 15 on the end here. Again, similar situation to last time. The last 2 terms are the only ones that are like. So final answer, -3x squared minus 4x minus 27. Final answer. All right, last example, g of f of x. They already wrote it in that form that I prefer, so I'm just going to remind myself f gets plugged into g. So that means g is my donut and f is my jelly. So let's go ahead and set up our donut. I do want to remind you, because this is our last example, that remember, because I have an x here, I know that I'm going to get an expression as my final answer. It's going to change in the next part of the video. So g is our donut. So everywhere I see an x, I'm going to put a set of parentheses. And this time, this example is a little bit more complicated because I've got 2 x's here, and this x is also squared. So just be careful. So you've got 3. Replace that x with a set of parentheses, squared, minus, again, since this is minus, I'm going to write that as a -1 so that I don't forget to distribute, minus, and then I'm going to put my set of parentheses, and then I've got minus 12 on the end here. All right, now that I made my donut, I'm ready for my jelly. So let's insert my jelly, which is -4x minus 13. Yes, you are going to fill this donut twice. I guess he's a special one. All right, so -4x minus 13 is in there. And now again, it's just a matter of order of operations, combining like terms. Common mistake here, guys. You're just going to go ahead and distribute that 3. No, 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 no. You're going to make a big boo-boo here. Remember, exponents come first. Squared means I have to write this out twice and FOIL, okay? So I've got 3 times negative 4x minus 13 times negative 4x minus 13. I'm going to distribute this negative 1 just to do a little bit as I go. So that means I'm going to get plus 4x plus 13. And don't forget about your minus 12 on the end there. Now these two guys here, I'm going to FOIL what I've got, and I'm going to keep that 3 out front. So I've got 3 times, and when I FOIL, I get 16x squared plus 52x plus 52x plus 169. And then don't forget, I've got these guys here. So I've got plus 4x, and these guys are like terms. 13 and negative 12 make 1, so I am going to combine that to just reduce as much as I can as I go. Now I have to distribute this 3. To save myself a little bit of work, I am noticing these guys are like terms, so I'm just going to combine them to make 1 term so that I can distribute over 3 terms and not 4. So this would be a 104x if I combine them. So now I'm going to multiply these 3 terms by 3. So if I do that, I'm going to get 48x squared plus 312x plus 507. And then I've got these guys on the end here, plus 4x plus 1. And I know what you guys are thinking. Oh my gosh, Miss A, we just got the biggest numbers ever. We must be doing something wrong. Stop it. Be confident in yourselves, guys. All right, so now I have no more order of operations to perform. I just have to combine like terms. So I've got 48x squared. I'm going to combine 312x and 4x to give me 316x. And then I've got 507 and 1 to combine to give me 508. And we are done. All right. So that concludes part 2 of this video. I suggest you take 2 days to work on those topics, and you go into Delta Math and complete composition of functions with X. Please be careful. Click on the one that says with X. All right, guys, so that they're the same. Also, for my kids, quizzes are available on the Google Classroom. Go ahead and check them out, and let's challenge ourselves this week. Come on, you guys have got this. All right, part 3, last part, similar to part 2, except we're going to kick it up a notch, and instead of making jelly donuts, guys, we are going to make turduckens or pie-cakins. Please tune in to my next video for the week to learn more about turduckens or pie-cakins, but long and short of it, what is a turducken? Apparently, this is a very famous dish that some people eat at Thanksgiving. It is a duck that gets stuffed into a chicken that gets stuffed into a turkey all together in one. Look at that. It looks delicious. And then we've got pie-cakins. These are usually made with 3 different layers, so I just gave an example. Sometimes it's layered, sometimes they're inside one another, but either way, it could be a cookie that gets stuffed into a pie that gets stuffed into a cake. And that, my friends, sounds like a really good quarantine snack. So if anyone's thinking about making a pie-cakin, send in some pictures and let me know how it tastes. All right, so these are your turducken or pie-cakin problems, and I'm actually going to refer to all these as pie-cakins just because I'm kind of in the mood for something sweet right now. Turducken is not really my thing at this moment. So your pie-cakins, right? This looks the same as the problems before in the last part of this video, but now we've got not an X here, but an actual value. So that means that we're going to plug this value into this function and take that answer and plug it into this outside function. So we're going to do this in 2 parts. So working from the inside out, -1 needs to be plugged into our function f. So let's go ahead and do that. Everywhere we see a set of an x, we're going to put a set of parentheses. So 2 times a set of parentheses squared minus 4 times a set of parentheses plus 13. We're going to plug in that value of -1. And we're going to follow the order of operations. So remember, -1 squared, exponents come first, is going to give me a +1. So 2 times +1, a -4 times a -1 gives me +4, and then we've got +13. 2 times 1 just gives me 2, so 2 plus 4 plus 13 gives me 19. Now, we are not done. Okay, we are not done. We just found out that this is the value of 19. We now need to plug that into our function g, right? So essentially we plugged our duck into our chicken. Now we have to plug that into our turkey, or we plugged our pie into, or sorry, our cookie into our pie. And now we have to plug all of that into our cake. So let's go ahead and do that. We've got our function g left. So we've got 3, and then again, parentheses. So 3 times a quantity minus 3. That quantity is going to be that 19 that we found. So 3 times 19 gives me 57. 57 minus 3 gives me 54. This is your final answer. Okay, so it's not the 19 that we are entering in as like a final answer to Delta Math or circling on our SAT or our college entrance exam or whatever. It's 54 that we care about now that we're done. All right, last example. Again, different notation here, so I rewrote it in case that's visually pleasing for you, but here we go. We're going to plug 3 into our function g. We're going to take that answer, plug it into our function f. So our pie cake and cookie in the pie. So let's set it up. Again, there is a negative sign in front of this x, so I'm going to write it out as a -1 so I don't make a boo-boo. So I've got -1 times some quantity minus 4. That quantity, my cookie that I'm plugging into my pie right now, is 3. Now it's an order of operations deal. So we've got -3 minus 4, which gives me -7. But remember, we are not done, okay? That's what this value is, -7. We now need to plug that into our function f, into our cake. So our function f, everywhere there's a set of parentheses, we're putting that -7. So we've got 3 parentheses squared plus 4 parentheses plus 8. And we're plugging in that -7 into that set of parentheses and carrying out the order of operations. So -7 squared gives me 49. So 3 times 49. 4 times -7 gives me -28, and then plus 8. 3 times 49 gives me 147. I know what you guys are thinking. Oh my gosh, another big number. I must be doing something wrong. Cut it out, guys. Be confident. All right. 147 minus 28 gives me 119. And then if I add 8 to that, I get 127. That is my final answer. Again, that is what Delta Math is looking for. That is what your SATs, your math placement exam, whatever the case might be, is looking for, not this little guy here. Final answer here. All right, guys, I hope this video was helpful. Can't wait to see you guys in our Google Meets and chat with you next week. Good luck.